We are now going to talk about electrophilic aromatic substitution reactions. In this first set of slides, we will look at what to expect as products of these reactions and take a look at the general mechanism by which the reaction occurs. As the name suggests, there's a substitution. A hydrogen atom on the aromatic ring is replaced by an electrophile, symbolized as E+ here. The electrophile may actually be generated as an intermediate during the reaction mechanism. It may not actually be one of the reactants that you see. Also, when you see these equations written, you may observe the hydrogen as just H+, or maybe shown bonded to something like HBr, for example. Let's compare the reactivity of alkenes and aromatic hydrocarbons. As you recall, alkenes undergo addition reactions. Here you see, as an example, bromine added to 1-pentene. We did this type of chemistry in the lab this semester. Here we have 1-pentene with a pi bond between carbons 1 and 2, and when you treat it with bromine, you get an addition reaction. The pi bond is gone, and each carbon of the pi bond has now gained bromine. The results are different if you react bromine with an aromatic hydrocarbon. As you recall, you actually have no reaction if you just add bromine to an aromatic hydrocarbon. We did this in lab. But if you want it to react, you simply add a catalyst like ferric bromide, and an electrophile will be generated which is stronger and will cause the aromatic ring to react. We'll see that in the next set of slides. So we end up with a substitution reaction where the hydrogen is replaced with a bromine. So what is the reason for this difference in chemistry? Well, aromatic rings are more stable. We've talked about that before. They're more stable than alkenes, and that's because of the high degree of delocalization of electrons in the ring. We call that resonance energy. That makes an aromatic ring more stable, meaning lower in energy, and since it's more stable, it's less reactive. You therefore need a stronger electrophile. So the ferric bromide is a catalyst that itself is not the electrophile, but its presence allows a stronger electrophile to be produced. The reason for substitution versus addition is that when we have a substitution, the product retains aromaticity. If we did an addition reaction, this pi bond would be gone and the ring would no longer be aromatic and the product would be less stable. So let's look at the mechanism. It's a two-step mechanism, and the first step is the same as we saw for alkene addition reactions. A pi bond of the aromatic ring is the nucleophile, just like the alkene was for addition reactions. This nucleophile, the pi bond electrons, reach out to the electrophile. This pi bond pair of electrons is now no longer between these carbon atoms. The electrophile is now bonded to one or the other carbon atom. Here we see it's bonded to this carbon. The other carbon is lacking electrons now and has become a carbocation. If you look at this carbocation intermediate, five of the six carbons are sp2. They all have an unhybridized p orbital that are either being used for pi bonding or are empty for the carbocation. This is an sp3 carbon now. Note that there are 3 resonance structures where the pi bond moves around and the carbocation shifts location. This intermediate goes by several names. You'll sometimes see it referred to as the rhenium ion, the sigma complex, or the cyclohexadienyl cation. Step 2 is where the mechanism differs from alkene addition reactions. In step 2, a base with its lone pair of electrons reaches out to the hydrogen, forms a bond to it, as you see here. The bond between carbon and hydrogen breaks. Where do these electrons go? They move back into the ring to reform pi bond, and now we've reestablished our aromaticity in the product. The hydrogen that is taken is the one that is on the carbon that has the electrophile. Sometimes organic chemists will simply show this pair of electrons moving here, this bond breaking. The electrons move here to reform the pi bond, and they're more interested in just this structure, what's happening to it. So they won't always show, they know it's happening, but they won't always show the base doing this. And so the hydrogen simply comes off as H+. I say that because you may look at different videos online or look at different textbooks and see that kind of representation. So this scheme here shows the two steps of the mechanism with a comparison in step 2 of what would happen for addition versus substitution. Here in this scheme, Y plus is the electrophile, and step 1 is the pi bond reaching out to the electrophile. We form our carbocation intermediate. Of course, there's resonance. We're only showing this one structure. And then step 2 can go down 2 pathways. This species here with its electrons, the lone pair of electrons, can act as a base. Now, if it reaches out to hydrogen, that is a Bronsted-Lowry base. And as you recall, organic chemists would call that a base. When it instead attacks another atom other than hydrogen, like this carbon, the carbocation carbon, and forms a bond to it, that is a base also. It's a Lewis base, but organic chemists call that a nucleophile. So just to remind you, if it attacks hydrogen and takes hydrogen, we call it a base. If it attacks some other atom and forms a bond to it, we call it a nucleophile. So if it proceeds as a nucleophile, that leads to addition, which is what we saw for alkenes. That does not happen with aromatics. Instead, we go down this path where the species acts as a base, removes the hydrogen, and reestablishes the aromatic ring, which results in substitution. If you consider the thermodynamics, you can see a big difference between addition versus substitution. If we do a substitution reaction, it is actually endothermic because we have lost the aromatic stability in the product. If we do a substitution reaction, we retain the aromaticity and it is exothermic. This reaction profile diagram shows the 2 steps. You can see that there are 2 steps in the mechanism. In step 1, we have the slow step, the higher activation energy. And if the step proceeds, we get our intermediate, the carbocation intermediate, 1 resonance structure shown here. Now, if you only have bromine, this activation energy is so high that the reaction is incredibly slow. So what we usually do is add some reagent to generate a stronger electrophile. What would make it a stronger electrophile? It being less stable, higher in energy. So we raise the energy of the reactants. And what does that do? It decreases the activation energy, makes the reaction go faster. In step 2, we can proceed to an addition product or to a substitution product. If we proceed to the substitution product, the product is lower in energy than the reactants. We have a net exothermic process. If we instead go to the addition product, it is an endothermic process. The product is higher in energy than the reactants. So in the next set of slides, we'll be looking at specific reactions of this type. Halogenation, we sort of touched on that with bromine, but we'll look at it in more detail in the next slides. Adding a nitro group, nitration, adding a sulfonyl group, sulfonation, and a very useful thing is to add carbons, make new carbon-carbon bonds and make the molecule bigger, and you can do that by alkylation or acylation.